All right, everyone, let's get started. Can one of you guys confirm that you can hear my audio and there's no audio glitches at the start of today? Thank you, Hannah. So, hello everyone. My name is David Ruck. I'm here at the University of Maryland in Baltimore, Maryland, and welcome to Cytometry in R. So, as I was caveating, we had some audio issues yesterday. So, if you hear any weird Geiger counter sounds of clicking, please let me know. I found a fix. I don't know why it works, but the sooner I know about it, the less we're going to have that clicky, staticky sound in the recording. So, today we're talking about gating sets. Now, we are now within our fifth week of the Cytometry in R course, and this is exciting because it means we're through a significant portion of the introductory to R material. That doesn't mean we're not going to be seeing like base R or just like general R knowledge throughout the rest of the course. We're still going to be seeing it, and we're still going to be adding new functions every single week. But we're now going to be turning it more as far as the cytometry focus, looking especially at like how do we interact with cytometry related data sets, how do we do cytometry related applications. So this first week of gating sets is that initial pivot where we start looking more and more at the cytometry side and less more at the introductory material in terms of R. So if we are thinking in a context of our regular flow cytometry experiments, there's a lot more to our analysis than simply acquiring the FCS files. So even though there's a substantial amount of information that we can find within the individual FCS files, kind of like what we saw during the third week of the course, if you're thinking what the commercial software is doing, it also has infrastructural elements that allows it to organize the particular files, to transform the data, i.e. to scale it, if you're working with conventional flow cytometry files, to compensate it, also to visualize the data, derive statistics, and a few other different things. So if we're thinking about what infrastructural requirements we would need in context of R to be able to handle many of those same kind of functions, we're primarily looking at two R packages from the Bioconductor repository, namely flowcorp, which we've been introduced to already, and flowWorkspace, which we'll learn about how to use today. So we're going to be building off of where we left off with week 3, where we saw how to load in our contents of our FCS files into R as a flow frame, and we're going to continue from where we left off and build a solid foundation that will allow us to explore in greater depth how we're able to combine these different components individually into a workflow that's kind of similar to what we're already doing, but just within the R context. So a little bit of housekeeping as we do every week. I have updated the course repository with this week's dataset and this week's course materials. So if you haven't already, please go ahead and sync your forked version of the Cytometry and R course folder just to bring in all those recent updates. And then once you're within Positron, just go ahead and pull in those changes locally. I'm still behind on those take-home problems, so if you are one of those people with the merge conflicts, please follow either the walkthrough to resolve the issue, as well as the updated homework submission procedure going from branch to branch is also detailed here. If you're following the structure of organizing things for the course, you'd need to create the Week 5 project folder. I'll go ahead and copy the contents of that data folder from the Cytometry and R local version into your Week 5 project folder, just to make sure that you're not running into any merge issues, trying to bring in next week's data sets. And then once you have all those subfolders organized and are ready to basically start fresh from where you're at, remember to make a commit and then push those changes to GitHub so that you're able to continue to maintain the version control. All right, so let's recall what we left off on week 3 as far as bringing in our contents of our FCS file into R in the form of a flow frame object. So the way we were doing this is we first needed to identify where our FCS files were by providing the file path between our working directory and the actual folder in which they were found. So if you're following the same kind of organization scheme that we're currently been maintaining for the course, if you have all those transferred in, copied over FCS files within the data folder, you just start building your file path dynamically using the file.path function, and you're assigning it to this little variable we're calling folder. And then we're using the list.files function, just basically using it to check within that folder location, find any files that match the pattern .fcs, and then keeping full.names argument set to true so that we have the full file path between our working directory and those particular files. So you can see the data set for today, we have 6 files total. They're looking at the cord blood specimens that we've been working with for the last couple of weeks, primarily the tubes that were either the control tubes or those that were treated with SEB. So now that we have identified out the FCS files that are contained within the folder, if you're trying to select just one of them to use with the read.fcs function, we can use that square bracket notation we've been seeing throughout the course just to kind of select based on the index value of that list which of the SCS files we want to work with. So in this case, we're selecting the first item in that vector, which is infant52, the control well for that particular FCS. So we need to be sure that flowcore is attached to our local environment. So we're going to do that via the library function, just like we've done every week. That will, if you're doing the toolbox analogy, open the toolbox so that we're able to get in and access all the tools, i.e. all the functions that are inside. In this case, we want the read FCS function. So once we have libraried flowcore, if you remember back to week 3, read.fcs takes 3 arguments. We're providing the file path to a particular FCS file, in this case, FCS_files, square brackets 1. And then we're keeping the truncate max range and the transformation arguments set to false, as we kind of explored why back in week 3. And sure enough, at this point, we have read in a type of object which we know as the flow frame, which we explored back in week 3. We can see it has quite a few floors in this case, and you can kind of see under the description slot, the individual little markers are appearing as well, which wasn't the case back in week 3 when we were exploring a raw spectral flow cytometry file. Now, if we're thinking about in the context of that wider infrastructural gain of what we're trying to do with our files, we're going to be working with multiple files, not just individual ones. So what would happen if instead of passing a single file path to read.fcs, we're passing the entire vector of file paths to read.fcs? So obviously in R, we can test it and we can check. So if we did that right now, and instead of subsetting using the square brackets, we left FCS files intact, we're going to get back an error that looks like this. File name must be a character scalar. Now, if you're thinking about this, this is not particularly interpretable at first glance, but what's basically happening is the type of object that we're passing to that function is not matching with what that function expects to have. So if we're thinking of functions as tools, and we think that particular tools need particular types of objects in order to work, i.e. a hammer needs a nail, a paintbrush needs paint, we're basically passing a nail to a paintbrush and expecting it to work. So as far as what that scalar was meaning, it's basically if you're thinking of our FCS file paths, when we bracket it into having just a single item, it's a single value. That is what is known as a scalar. So read.fcs requires a single file path to be passed, but when we end up passing it the combined vector, it's not matching with what it expects, and that's why it errors out. And this is what we'd see, for example, if we're looking at what's actually within FCS file underscore files, it's all that little vector of file paths. So that's why it errors out. So consequently, if we're trying to work with multiple FCS files at once and not just one file, one file, one file all across the board, we need to use a slightly different function when it comes to reading in that data. So if you're thinking in the context of the flowcore package, instead of read.fcs, what we're going to be using is its sister function, read.flowset, as the function. And it still keeps all the same kind of arguments. In this case, we're passing files. As the argument files, we're passing it FCS_files, which is our list of file paths. And we're keeping this other 2 arguments still set to false. In which case, as you see, we read it in, we're assigning it to a new object, a new variable in our environment, which we're calling flowset. And when we are printing it within a console, we can see it shows up as a flowset containing 6 experiments, and then it lists the common column names for all the files. Alternatively, if we wanted to only take some of those file paths that were within FCS_files, we could use the square brackets and a little C, which stands for concatenate, to kind of like select which ones of the file paths we wanted. So if we only wanted to grab the first and then the third through the fourth files within that vector, this is the kind of designation we do to basically select some of them and use those to be read into our R environment. So if we decide to use those type checking functions, which we learned about over the last couple of weeks, both str and class, if we run class as it currently is, we see we're getting back a flowset, which is also encoded within the flowcore package. And if we're following up with our exploring troubleshooting skills that we learned over the last couple of weeks, If we look over on our right secondary sidebar, we can see that we have the new flowset variable we have created. We can see it's one of those S4 class objects from Bioconductor. Specifically, it's a flowset. We can see it has 2 slots. Checking down on the drop-down arrows, we can see the slots are frames and pheno data. And if you look at each of the individual little frames, we see that those 6 FCS files we read in are present, and each of them are appearing as an individual flow frame with the tree respective slots that we looked at during week 3. So basically, flowset is working kind of like a container object that will contain the flow frames, which we have much more experience working with. Now, instead of using class, if we had used str for the console command, we could have seen something very similar, but just be appearing within the console. In this case, we just have to remember each of those slots is denoted by that little @ symbol, and then the number of tabs basically is what's delineating how far down the hierarchy it actually is present at. And as a reminder, it's not our focus for today, but if we were trying to access individual components within a S4 type object like the flowset, we just have to write the flowset name and then the particular @ symbol and the name of the slot to be able to extract out that underlying data. All right, so both flowFrame and flowset objects were first implemented in the flowcore package, which, as we saw, is the oldest extant flow cytometry package within Bioconductor, being about 19 years old at this point. Consequently, a vast majority of the R packages that are working with flow cytometry and data in R are able to handle flowFrame and flowset style objects. Now, one consideration of using this method is you're actively reading in the contents of your SVS file into your computer's random access memory or into RAM. So in the context of most individual, if you're working with just individual FCS files or just very small experiments, this is not going to be a problem for most modern computers. But you may be running into some issues if you're working with very large spectral flow cytometry files with like 40 different parameters and like 3 million, 4 million cells per individual FCS file, or if you're trying to work with like hundreds of thousands of FCS files all at the same time. You may encounter that as you try to read in all your data set into your active RAM, you don't have enough RAM for your particular computer and you end up crashing the system. So, to try to build a little bit of contextual understanding of what this problem may look like, I want us to be able to tell like what do individual variables, i.e. individual objects within our R environment, actually take up in terms of space. So if you're using base R, we can use the object.size function to kind of check that, but it's not the best, especially for like nested S4 style objects. So what's better to use is if you go on CRAN and install the lobster R package, you can use a very similar kind of function. In this case, instead of dot, it's underscore for size. And that will be able to more accurately see how much each individual variable is taking up of RAM on your computer. So if we go back and just go ahead and double check for flowFrame using the base R function object.size, we can see it returns as 3.57 megabytes more or less. However, if we're using the lobster function, lobster package, once we've attached it to our local environment via the library call, and we check object underscore size, we can see that, yeah, the flowFrame occupies about 3.53 megabytes total. And this is a substantially downsampled FCS file. I think I only kept maybe 10,000 cells within this particular file. By contrast, if we think of our flowset object, which has 6 individual flow frames within it, if we go ahead and check to see what the object size is using that object underscore size function, we can see it's occupying about 21 megabytes of memory within your system right now. So right now, not very much. I'm at no risk of being able to max out my particular system, so we're so far so good. However, if you're thinking, okay, these are individual files within my R environment, but how much do all these different objects I've already created at this point in my workspace add up as far as total memory being used? We can use the mem underscore used function to be able to see what's actually present. So we can see at this point in my workflow, I had used up about 147 megabytes of space on my actual computer at that stage. So ultimately, how many FCS files you're able to read in and interact with before you run out of available RAM on your particular computer depends on your computer's individual hardware configuration. There's a lot of different ways you can go and check to see how much RAM your computer actually has if it's something that you don't remember off the bat. The specific functions that you'll use will vary depending on your computer operating system, since they often involve system-level code that's outside of R. However, in the process of getting set up for this particular week, I found the PSR package, which is available on CRAN, kind of does a good method of handling across systems. So if you're just trying to use up and get a easy result, this is what I would recommend. And basically, if you're thinking of trying to use the more system level calls, this is a good situation where we can call back to week 2, where we use what we knew as a conditional, which is basically a way of if a certain criteria is met, it will run a certain amount of code that's within the curly brackets. So sys.info is a base R function, which will just basically return, is it a Windows computer, is it a Mac OS computer, is it a Linux computer, and that we can use within the conditional to kind of designate which function should be run depending on what your computer operating system is. So in this case, using that sys.info, we're basically taking that list that gets generated by this function, and we're looking for the system name variable that's present in the list. So if you're on Windows, it's going to show up as Windows. If you're on Mac OS, it's going to show up as a variable that's showing up as Darwin. If you're on a Linux operating system, it's going to come back as Linux. So whatever computer you're running at that point is going to return its particular variable name, and it's going to be assigned to operating system. So if you remember back to week 2 where we worked with that conditional, basically if operating system, which is whatever's being stored in this variable, is double equals to whatever name we're giving it. So in this case, let's say we are on a Windows computer. The operating system variable is going to come back as Windows. It's going to actually equal Windows. So this entire sentence here is going to get evaluated as true, which means this conditional is met and everything within these curly brackets is going to be actually run and passed to the console. In which case, it's going to use the PS package. It's going to check system memory. It's going to return the total amounts of gigabytes of RAM that your computer has, as well as how much of it is currently free and being able to be used. However, let's say you're on a Mac OS, it's going to show up as Darwin within the operating system variable. That is not equal to Windows, so this condition is going to be false. But this is where we can do a slightly different version of the conditional. And then if we add else if immediately afterwards, it's going to continue on to this next evaluation statement, in which case, if your operating system's variable value is equal to Darwin, which would be correct if you're on Mac OS, it would run this little individual line for your Mac OS system to just check to see what actual physical memory you have. Vice versa, if you are on Linux, this would evaluate as false. It would jump down to the very next one, check, and then be able to run the system level command. So this is an example of a little bit more complicated conditional if you're trying to have yes or no and going off on multiple directions for different lines of code. However, if you don't want to mess with the conditional, the PS package does allow the same kind of handling behind the scenes, and you can just kind of follow the same line of code just to figure out how much memory does your computer actually have in terms of RAM. So, in addition to the flowcore R package, there's additional flow cytometry infrastructure support that's provided by the flowWorkspace package. And it's a little bit newer than flowcore, not by much, by a few years. But it takes a slightly different approach when it comes to interacting with your FCS files. So unlike the flowcore package, which reads everything into active RAM, what flowWorkspace does is it works through what's known as pointers, which are beyond the scope of trying to explain for this course. Basically, think of it's pointing at the object wherever it happens to be currently stored. So whether it's on your hard drive, your solid state drive, whatever version of a memory you're using, and it's only actively reading in contents for those particular files at the moment that they're actively needed. So instead of basically preloading everything into your RAM, it knows where the data is at, and then it will go find it when it actively needs it for whatever particular task you're trying to do. So to be able to use this, you just need to make sure you have flowWorkspace installed from the Bioconductor project. You attach it to your local environment using the library function. And then, just to keep things simple, you have the same kind of equivalent loading in of the SCS file individually or as a group. So it's going to have a slightly different function name in this case. Instead of read.fcs, which we saw in flowcore, it's going to be load underscore cytoframe underscore from underscore FCS as the function. So which is quite a wordful, but at least you can kind of get the picture of what this particular function does directly from the name, which is quite useful. In which case, it's still keeping pretty much the exact same syntax as far as arguments that we saw for read.fcs, but it's loading it in, and as you can see, when we print the object's name in the console, it's showing up as a cytoframe object. It shows similar information as far as the number of cells, the number of columns, and some other sets of information across the board. And sure enough, if we check the class function just to see what it is, we can see it's showing up as a CytoFrame, which is being defined within the flowWorkspace package. However, if we still try to pass it a actual vector file path instead of an individual file path, we're still going to get a scalar kind of error where it's saying it's expecting to see your vector come back with a length 1. So this is just one of those things to always remember. Are you working with a flow frame? Are you working with a flow set? Or are you working with a cytoframe or its equivalent? In which case, the equivalent in this case would be a cytoset if you're trying to work with multiple FCS files, but using the pointer system instead of trying to actively load them into RAM. And sure enough, once you load them in, we can see there's 6 samples present within this cytoset, and it's listing the common column names between all those FCS files. And if we check class cytoset, we can see that, yep, it's appearing as a cytoset. So, as I mentioned, unlike flowFrame and flowsets, when we're checking cytoframe and cytoset, these are not actively being loaded into RAM. So when we check them using str, they're going to look a little bit different. So if you can kind of see, the slots that are denoted by the xpers, where we're normally going to be seeing our MFI data, are currently empty. There is a matrix defined, but it has 0 rows and it has 0 columns. And same thing when we're talking about those parameter data frame back in week 3, we see that it's not actually loaded in. We don't see the names. We don't see the description. We don't see any of that range information. It's not actively within your R environment. It's just the actual pointer itself. So similar thing happens when you look at the cytoset. It will show you there's different FCS files present, but it's not any of the actual data you would see in the context of a flow frame or a flow set. And if you looked at your right secondary sidebar, you can kind of see it's being occupied by little question marks or empty environment. It's not actively being filled out like we saw for a flow frame or a flow set. So because of this, it's able to use substantially less RAM. So let's go back to those memory utilization functions we just looked at and see what it actually looks like in the context of our individual files. So if we use object underscore size, we can see that the flow frame object, which is actively being loaded into RAM, is using 3.53 megabytes. However, if we're loading in that exact same FCS file, but as a cytoframe, we see it's only occupying 5.4 kilobytes, so substantially less space being occupied within your RAM at any given point in time. And this is similarly the case if you're checking your flow set or your cytoset objects. The flow set itself, as we saw, was 21 megabytes more or less. But when it's loaded in the form of a cytoset, just using those pointer systems, it's only 3.8 kilobytes. So if you're working on a system that doesn't have very much RAM, or if you're working with a massive amount of files that you don't want all present in at the same point in time, using the cytoframe or the cytoset approach is a much better way of going, just because you're going to be able to work with all that data. You're still going to be able to process with it, but you're only loading it in as you actively need it, not keeping it all front-loaded and loaded at the same time. So, one of the reasons this wasn't the original approach was back 20 years ago, we were still mostly relying on spinning hard disks as our main form of storage on our computers. This has been replaced by those faster solid-state and NVMe drives. So what used to be the performance penalty of trying to work off of something that's on a hard disk is no longer quite as much of a concern as it was in previous years. However, at the same time, our main limitation as flow cytometrists is we're working with really large files, not so much. We're working with really large files and very generally not as much RAM compared to the individual file size. So as long as we're able to do it, it's more important than trying to do it quickly and running into errors in the process. However, because flowWorkspace is using a new different type of object, i.e. the cytoframe and cytosets, not all the R packages on Bioconductor are able to interact with these types of objects. So oftentimes, if they're only able to work with flow frames or flow sets, if you pass it a cytoframe or a cytoset, it's going to provide an error out symbol, kind of similar to if you provided the wrong type of object. So it's one of those things that as we go throughout the course, we need to be aware, is this particular R package able to handle a cytoframe, or is it able to handle a cytoset? Fortunately, we're able to interconvert readily between each of them. So the functions of them are kind of intuitive. So if you want to go from a flow frame to a cytoframe, you're able to use that equivalent function. And sure enough, it converts it over to a cytoframe. And you can see it's now occupying far less space of RAM. Vice versa, if we wanted to go from a cytoframe to a flow frame, we're able to do so. In which case, we're going to have much more RAM being used. Vice versa, if we're trying to go from a flow set to a cytoset, sure enough, we read in those 6 samples. They're occupying substantially less space. And vice versa, if we're trying to go from a cytoset to a flow set, we're able to interconvert pretty readily across the board for all these objects. Fortunately for all of us, this is where the discrepancy and those parallel paths of either in RAM or on a memory pointer system, they all converge at the next step, which is loading in your FCS files, passing them off to the gating set function. So if you want to see, for example, loading in a flow set to the gating set, this works. Vice versa, if you take a cytoset and pass it to gating set, it also gets converted to a gating set. So you don't have to remember the differences once you get to this gating set point. So, as we preface in background, outside of the FCS files themselves, we need that infrastructural element if we want to work with the underlying data, but also to organize the FCS files, transform them if need be, compensate them if you're working with conventional flow files, visualize, derive statistics, etc., etc. So a gating set is basically that infrastructural framework when we're working in the context of R, especially within a flowWorkspace style framework. So we need to start investigating what we can do with a gating set object. So if we check it right now using our str or class function, or just looking in the right secondary sidebar, we're not going to see very much as far as information currently visible. However, as we start layering on additional elements, we're going to see this change over time. However, rather than trying to cram all those infrastructural elements that the commercial software does in those less than half hour that remains in the course for this particular week, I'm going to try a different approach. Namely, we're going to load in a already existing gating set object that is fully assembled so that we're able to evaluate what it's able to do, how it works as infrastructure, so that we then know as we go over the next couple of weeks and we start building them ourselves from scratch, what all these different layers ultimately are going to try to do. So the way we're going to do this is we're going to use the CytoML R package, which is a sister package to flowWorkspace. It's also maintained by Mike Jung. The main thing it does is it enables you to bring in already existing manually gated workspaces from Flojo, from Diva, or from Cytobank. Bring in all their gates, all their transformations, all their compensations, etc. into R as a fully assembled gating set that you're then able to use. So if you're using any of these commercial softwares, it can be a quite useful tool as far as being able to do semi-supervised workflows in both your commercial software of choice as well as within R. However, since this is mainly a class that we're focusing on how to using this particular R package, namely CytoML, we're going to be using a Flojo workspace that we're going to bring into R. However, since this is a free cytometry in R course, and I'm not about to have everyone pay for a license just for a one-off topic, just so you can learn how to use a single R package, I did in a pre-course walkthrough show you how to use flowRiata.io, which is a free web-based browser that will allow you to do gates and then export them as Flojo workspace files that you can then bring in with CytoML to kind of replicate some of the workflow that we're doing today. Although as I was testing it this week, I noticed there is a scaling bug that I wasn't quite able to fix, which might require a little bit of troubleshooting on your end, although your gates are still being created and still present. So to get started, we need to make sure that CytoML, the R package, is actually active in our local environment. So just again, we're going to need to use that library call. And once that's done, today we're going to be bringing in that Flojo workspace we had created, but passing through that flowRiata.io. And the main difference as far as the two workspace files that I included within our dataset is one's that original one, just directly created, exported from flowRiata, just being brought in directly. The other one I actually opened within Flojo after I had logged in with my license, and I ended up switching logical to the bi-exponential transformation just to make sure everything worked for particularly today. Now, just like we do with our FCS files, we need to make sure we're working in the correct folder that has those workspace files, and we need to actually list them in their file paths so that we're able to use them. So we're modifying our list.files argument. It's still working within that particular folder, but instead of FCS files, we're having it spot anything that ends with .workspace. And we're getting back to two Flojo workspace files, in this case the open copy, which is the one we're going to use for today, and then the unopened one, which is there for testing. So if we want to grab that one that's opened, we can do something similar to what we did with file paths back in week 2, and we can use the stringer packages structure detect function to basically check the existing items that are within the file paths that we return, find anything with the matching pattern of opened, and only keep that file path so that we're able to use it. So if you're trying to remember what this exactly looks like, we're using those square bracket notations. We're passing it to structured detect from the stringer package. We're having it search our existing vector of file paths and only keep anything that matches the opened. And you can see we've subsetted down so we only have that single file path that we're interested in. Now that we have that, we can pass it to the first cytoml function, the open underscore flowjo underscore XML function, which is just going to initially make sure that it is a workspace and check to see are there different groups, how many specimens are present, and you can see it gives back this kind of readout when we print it to the console, and it's showing up as a flowjo underscore workspace type object. This intermediate, we then are actually going to load into R to bring it in as a gating set. So this is where the second cytoml function, flowjo underscore to underscore gating set, gets loaded in. Or at least that was what we actually should try. However, when we set this up initially, we got back an error. And as you can see, it says multiple FCS files match the sample name, control.fcs by file name, event count, and keywords. So remember, for the dataset that I provided everyone this week, it was all the samples were different in terms of the group name, but they all had similar sample names. Namely, they were either control or they were SEB. Also, I had downsampled all the individual FCS files, so they all had all 10,000 events across the board. So at this point, R, and specifically the cytoml package, thinks these are just duplicates of each other, which is why it's coming back with that error. So if you're trying to actually read them in to our actual R environment, we need to be able to troubleshoot this particular error so it doesn't think everything is named control or everything is named SEB, but actually is able to check the group name variable to see that these are indeed different files. So this is a good example of like how I go about my troubleshooting. So when I get back this error, I'm like, okay, this is not working as I was anticipating. The first thing I try to do is I need to check the help documentation. So as you remember, if you're working within Positron, you can just hover over the function if it's within a code block. Otherwise, just a little question mark in front of the function name. And this will open up the help documentation. And as you can see, there's a lot of different arguments present for this particular cytoml function. However, after a little bit of perusing, I can kind of basically identify the additional keys argument, which kind of seems to be it's going to do what I want by appending a particular keyword after the name that's currently been read in. So if I provide that, the group name keyword, it should hopefully resolve the issue of everything being named control and everything being renamed SEB, and we'll actually be able to distinguish them as individual unique FCS files. And sure enough, as I'm setting up this argument, I'm adding that additional .keys argument. I'm saying add this group name to the end of all those names. And then basically it has that workspace intermediate object that we created. It's checking the path to that particular folder because it needs to actively load in those FCS files. The name argument's basically a workaround. There's a little pop-up window that appears when this is not present, so I'm just including it there for the code for today. And you can see it read in the gating set, and we now have those 6 FCS files present within R that we're able to work with. However, cytoml can take a while, so it's often a good idea to know how long it's going to take to load in your particular workspace. So if it's going to only take 30 seconds, you want to know it's only going to take 30 seconds. If it's going to take 30 minutes to load in all your FCS files, that gives you time to go make coffee, come back, and still wait a few minutes before it actually loads in. So there's a couple ways of checking how long does a particular function take to run. The main way you'll see is using the base R function system.time. And what this will look like is within system.times parentheses, you just add these little curly brackets around whatever line you're trying to evaluate. And then it's going to return how much time it took the user processing side, how much time did it take the system to read it, and then you can kind of see the combined time it took. So 0.59, I think it was milliseconds for the unit in this case. Likewise, there's also the bench package from CRAN, which is able to do it as well as repeat with iterations, just so you get a more accurate measurement. In this case, it's using the mark function, which once you have the bench package loaded into your active environment, you're doing kind of similar setup. You're having a line of code be evaluated in the middle, and then you're just specifying, hey, repeat this 5 times just so I have like the median amount of time this is taking. So you can see loading in the small example workspace from cytoml took about 556 milliseconds across the board as the median measurement. All right, so at this point, reflecting on where we're at, I had created a Floriada slash Flojo workspace, done all these different gates on my particular cells of interest. We brought those into R using the Cytoml package. And now I want to make sure everything was brought in correctly, that the transformations are still there, that the compensation is still there, etc., etc. So the very first thing is we need to double check to see how this is working in the context of our gating set. So I want to make sure my manually drawn gates did indeed get brought in correctly. So what we can do is there's certain sets of functions within our gating set that we can use to kind of see what's present, what is there, what can we use. And the first of these I'm going to introduce to you today is the plot function, which will just give you kind of like this little visual tree of the gates that are present for your particular gating set. So you can see it's kind of conventional. I did a scatter gate, I did a singlet gate, I did my live gate, I gated on some T cells, and then I took the different flavors of T cells, CD4, CD8, double negative, and I added a single cytokine gate to each of these respectively. So at this point, it looks like, yes, the gates that I had applied within my original workspace are still here when they're brought into R. But if we actually want to see this in a slightly different view, more on the console window side, we could use a couple of different functions. The one I'm going to introduce today is gs underscore get underscore pop underscore paths, which is this going to return kind of style of a file path arguments. You can see you have my root gate, my scatter gate, my singlet gate, all the way down to the little individual cytokine gates under each of the T cell populations. So this is a good way of evaluating are the gates there, at least as far as the initial structure. Likewise, oftentimes we're trying to get the counts for cells that are present within those individual gates. There are multiple ways of doing this within flowWorkspace. I'm showing you one of these today, and I'll show you more throughout the next couple weeks. The one for today is gs underscore pop underscore get underscore count underscore fast. If you haven't noticed at this point, flowWorkspace definitely follows snake case when it comes to how they name their functions. And sure enough, if I do this, it comes back and you can see it's all working off of the first sample that we loaded in. We can see the first set of gates, kind of similar as far as the showing of the file path. And then if we scroll down, we can see the actual cells that are present within each of these gates, as well as the parent count as well. Which, if you're looking at the homework problems at the end of today, is one of the areas you can use the mutate function to kind of derive what the frequency or proportion is for this particular gates. Additionally, if you're working with multiple FCS files, it's important that we're able to subset them based on metadata. So if you only want to look at SEB or you only want to plot the control samples, you're able to do so. There are a couple ways that we can check the metadata as well as bring in metadata. The main one is the pdata function, which will just kind of show you like this right now. So you can see that trouble that we had initially from Cytoml was because for a name, the first three are showing up identically as control, 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 and then the last three are showing up as SEB, SEB, SEB. But you can see there's some little row names that got created when we added an extra keyword for group name, and now it's just appending underscore infant 52, infant 100, which allows Cytoml to be able to designate between them. However, if you wanted to actually read in additional metadata, let's say your simulation conditions, your treatment conditions, etc., there's a couple ways you can add to this existing metadata that you can see with the pdata function. You can bring them in as a CSV file and then use tidyverse to kind of like append them on. Or additionally, we can use the additional description keywords and be able to bring them in individually. So let's say I went back to that original reading in with Cytoml of my gating set. You can see I can provide underscore date, $date, $site, all these different keywords we learned about in week 3, and it will appear as additional metadata columns when I actually go and evaluate. All right, so at this point we can surmise there's a lot of infrastructural style as far as elements that are present within a gating set that are similar to what the commercial software is able to do. One thing we haven't looked at, even though we're able to create and retain the gating information, how about visualizing the underlying data that's associated with each? And this is where the GG Cyto package comes in. So in the context of R, the vast majority of plots that you're going to see are using the ggplot2 package from the tidyverse, which we'll go into quite in depth the next time for next week. It builds on what's known as the grammar of graphics concept, which I've linked as well here, which basically by combining different layers and adding things onto existing plots, you're able to get many different types of plot outputs and be able to customize them extensively. In the context of flow cytometry data, the ggcyto-R package is able to do something quite similar for us today. Now, one important thing to remember, as is the case with most free open source software packages, Our packages will change over time as the developers add new features, make improvements, fix bugs, or just alter internal functions in an attempt to try to get things to speed up. So recently, ggplot2 from the Tidyverse went through a major version change, with significant internal changes occurring within the package. As a consequence of these changes, ggCyto, which relies on ggplot2, the way it had structured to do its particular things in the context of flow cytometry data, these functions ended up breaking and had to be updated in order to get them working correctly with the brand new version of ggplot2 that rolled out last year. As a result, we need to make sure that if you're trying to do ggCyto plotting of your data for this course, that you have both the current version of ggplot2 as well as the current version of ggCyto. Now, ggplot2 is not an issue because CRAN, basically, as soon as the developer updates the package, those changes are made available in CRAN, and you get them right off the bat. However, the Bioconductor project does a twice-yearly release cycle, and in order to take advantage of those changes that just occurred in ggCyto, which happened within the last month, you're going to need to install the developmental version to make sure that you have the compatible version on your computer. Because the stable release branch has not yet rolled over, has not yet updated, so you won't be able to benefit from those changes. So, what we should do for today is we need to make sure you have both the current working versions for ggplot2 and ggCyto installed on your computer. So remembering back to a couple weeks ago, we can use package version function to be able to check to see what package version is currently installed on your computer. So if we check ggplot2, you should have at least 4.02 or a greater version in case they release something newer that's covered by somebody reviewing the course later on in the future. And the package update for ggCyto that contained the bug fixes was 1.39.1, which is the developmental version of ggCyto. So if you retrieve the packages and you had both of those same package versions or a greater version for ggplot2, ggCyto, you're all set. You don't have to make any changes. You can just skip the reinstallation steps that we're going to go through right now. If you have one of the older versions, you can still try to see if you can run the code, but just anticipate it's likely to break because some of the changes made to ggCyto are not back compatible to the older versions. So if you had to go through the reinstallation steps, what I recommend is first is basically remove the two packages in question, just because ggCyto does have a hard dependency on the ggplot2 package. So if you're trying to remove a package from your R environment entirely, you're using the remove that packages function. In this case, just remove ggplot2 and remove ggCyto. And once that's done, I recommend just going ahead and closing out a positron and reopening. Just make sure that nothing's attached to your local environment and avoid some of those little kind of quirky errors that you might encounter in the process. However, remember, when you close positron, any lines of code that you had run, any variables that you have created are also going to be lost as the environment closes, so you'll need to be able to run them again to get back to the same point that we just left off at. The easiest way of getting back to the point you left off at, especially if you're working within a .qmd file, is to use these little run above options that appear directly above the code chunk. So basically, if you scroll back down to the current spot you are in your particular workflow document, just hit run above. Any code chunk that's currently present above that particular location is going to get run, it's going to get evaluated, it's going to create all its variables, all its objects that you're then able to interact with and work with. And once you're back down to the bottom, it's time to reinstall the two packages that you need. So remembering, ggplot2 is a rolling release model from CRAN, so you just need to install it just like any other CRAN package. So we're using the install that packages function in this case. However, if you need to get ggCyto, because it's Bioconductor's twice-yearly release cycle, you're going to need to grab the developmental version. Now, there is a way to do this via Bioc Manager, but since this is just a one-off package that you need to install, the easiest approach is just to use the remotes package and just install it directly from GitHub. So in this case, if you're going to grab the developmental version from GitHub, it's under the RG Lab account /ggCyto for what you need to download. And then hopefully at that point, you now have both packages that you actually need when it comes to terms of plotting. So go ahead and attach them to your local environment using the library call. And at that point, ggCyto is very similar to the ggplot2 grammar graphic syntax. This is stuff we're going to be learning how to actively use next week, but I don't want to leave you hanging without actually seeing plotting of flow cytometry data. So I'm just going to show you an example line of code and just kind of walk through the very basics of it today, Remember, any of the actual details, all the actual nuance, that's going to happen next week when we go into ggplot2. But basically, we're using the ggcyto function. And then the very first argument is basically we're using our gating set object we've created. That square bracket notation of ones designating we want the first FCS file contained within this gating set, which we can see using pdata as far as saying what that actually was. The subset argument is basically going to be where you're designating what gate you want visualized. So currently when it's set equal to root, it's just going to show all events that are contained within the FCS file. You're going to see all debris, all doublets, everything across the board that's present within the root gate. If I had instead set this to be live, we would only be seeing the actual cells that are contained within the live gate. If I had set this for T cells or CD4 or CD8 T cells, it would only be showing that respective population. Aesthetics is what stands for AES. We'll talk more about that next week with ggplot2. But basically, it defines what's on your x-axis and what's on your y-axis for a particular plot. So in this case, since I'm looking at root, I just want to say the forward scatter area by the side scatter area. And this first section here that's being evaluated is just basically finding the data that you're actually going to be using to plot, designating what's going to be plotted. But then within the ggplot2 grammar, graphics, syntax, which we're covering more next week, it will basically add in an additional layer that will actually carry out the plotting. So in this case, for flow cytometry data, we're using geom hex function, and we're basically specifying the number of bins as 100. We'll see what this does in just a little bit. And we're basically appending this on to the data with this little plus symbol, remembering the details we'll cover as we go into next week. And this was basically the walkthrough of that same description I just gave you guys verbally. But if all works out and you have the correct version of the packages installed, what you'll end up seeing is a data that plot that looks like this. So you can see the aesthetics, forward scatter, side scatter are being defined on our x and y axis. We're looking at the CD4 population as far as what's being printed. You can see it's also appearing within the label at the top of the plot. It's using the very first specimen. And as you can see, bins was defined as 100. So you can see these little hexagons on the plot itself. This is what's being used as bins. So if you set bins to 10, there's only going to be like 10 bins. So it's going to be, all your cells are going to be kind of assigned to one of the bins or the other. If I instead set that to 10,000 bins, this would be like each cell would have its own little bin. And this kind of will also impact the little pseudo-color appearance as far as the heat map values that you see present in the plot. So this is something you can play around with until you get it to the right level of granularity that you actually want to show for a particular plot, a particular style. Now, let's say we started messing around with the little arguments, just switching things around. So let's say instead of CD4, we wanted to look at our CD8 population. And instead of the combination we had on the axis of forward scatter, side scatter, we wanted to look at interfering gamma by TNF alpha. So aesthetics will accept either the fluorophore name or the marker in question. So in this case, I'm using the marker name to designate what I want on X and what I want on Y. And this was a control specimen, so you can see there's not very much interfering gamma beyond the background noise that we're seeing for the particular marker. Likewise, if we didn't remember what a particular marker was, we could just use the fluorophore name. So in this case, same exact example. I'm just using BB750 as the argument within X and PDAZZLE as the argument within Y. It's plotting the corresponding amounts. You can see the actual specimen name, which corresponds to GS brackets 1, is being shown here. And just remember you, this is just the very base layer of the plot. We can do a lot more customizations, and we will over the next couple weeks. So if you don't like the gray background, if you don't like the label being in the far left side, you want to move it to the center, these are all the things that using grammar or graphics, we're going to be able to customize and edit as we go. Then if we don't want it as zoomed in on the population and want to make a little bit more of the scaling kind of appearance we associate with FlowJo or FCS Express, we're able to do so as well. And likewise, just checking my T cell subsets. If I wanted to check CD4 by CD8, I can see that, yep, the data is plotting. And it appears to be kind of bi-exponentially transformed, as I had specified in this case. You'll notice when you're working with flowWorkspace and ggcyto, it doesn't show you the exact same kind of tick marks you'd see like in FlowJo. It's going to show you more of a linear transformed actual values when you're interacting with it. And that's all we're going to be able to cover for ggcyto for now. Remember, we're going to be circling back to this extensively over the next couple weeks, both next week as we talk about ggplot2, but especially the week after when we're actually seeing how different transforms affect our individual data set. So this is going to be something you're going to gain a lot more familiarity with over the course of time. If you want to jump ahead, you can just go down to the additional resources section. I've linked the vignettes of how to use the ggCyto package, so you can play around and customize things as you want. You don't have to wait on me for tinkering in this section. All right, so our takeaways for today, we've looked at the two main representations of flow cytometry data within R, both the older flowcore implementation of flowFrame and flowsets that stores things in active RAM, as well as the flowWorkspace implementation of cytoframe and cytoset objects, which use memory pointers and only load things into RAM as they're actively needed. So we have started to learn how to use getting set objects, starting off with a fully assembled object, which we'll build on and learn how to build individually step by step over the next couple weeks. And this gating set object is what allows us to do a lot of those infrastructural steps that is normally handled by our commercial software. And finally, we looked a little bit of an introduction of how to use the ggCyto package to be able to visualize the data that's contained within our gating sets in a particular gate, a particular node kind of fashion. And just like we saw a little bit for last week with the tidyverse functions, gating sets is something we're going to continually revisit throughout the course. So just like we're going to be using dplyr for the next 25 weeks, we're going to be using the flowWorkspace package pretty continuously over the next 25 weeks. So this stuff you'll gather as far as exposure with each subsequent time. We also looked a little bit at how to use the Cytoml package. If you are one of those people who uses FlowJo, Cytobank, or Diva to bring in data workflows into R, it can be useful. Next week, we're going to talk about the ggplot2 package from the tidyverse, which is where the grammar graphics concept is first implemented. We're going to see by how combining these different layers, customizing the arguments, changing the elements, we can build a lot of different types of plots, not just flow cytometry plots, but also the plots we use as far as reporting data, statistical analyses, etc., things that we'd actually use in the context of a publication. And with that, we're closing in at the top of the hour. If anybody needs to leave, I'm appreciative of your time, so I can let you go. The additional resources for this week are pretty vignette heavy because Bioconductor packages do a very good job as far as documenting how to use them. So if you want to learn more about flowWorkspace, either the cytoframe, the cytoset arguments, the gating set, and all the 100 different functions that you can use with the gating set to retrieve or do particular things as far as the infrastructure side, flowWorkspace vignette is the first place to stop. If you are one of those people using FlowJo, Diva, or Cytobank routinely, the Cytoml vignettes are good to be able to figure out how to customize it for your particular FCS files, for your particular use case. ggCyto has a lot of vignettes to be able to do a lot of specific customized style plots. So I refer you to the website if you want to be able to figure out how to do that. It's stuff we'll be covering over the course of the next couple of weeks as well. And then back in the Bioconductor conference in 2023, which was in Boston, a set which kind of maintains a lot of these Cytoverse packages, did a workshop as far as how to use flowWorkspace, how to use ggCyto, etc. So I linked the workshop. It's about 2 hours. We're not covering all the contents that are present already. Some of this is stuff you'll be exposed to over the next few weeks, but if you're dying to learn more and want to see it in an audio format, this is why I refer you back to. The take-home problems for the next couple weeks is kind of like similar to what we saw last week with the tidyverse. We ended up with the pdata function. We saw there was particular sets of column names that are present, but then also we had that function that returned the actual cell counts for particular gates. So kind of combine what you learned a little bit about last week. I want you to try to mutate and figure out what the percentage of the parent gate is from those initially retrieved out column counts. This is going to be a little bit tricky, especially for you getting started. It's something I'll show you how to do way more efficiently over the next couple of weeks, especially when we get to the statistics focused lecture. As we saw today, Cytoml can be finicky, especially where those names are repeated. So if you're working with your own data set and you already have a workspace created, kind of play around with it on your end, or if not, just tinker with the ones I provided. Take away FCS files, put FCS files in a different location, see how you can break it so you're a little bit more familiar with how to use the particular package. And then the third one for ggCyto, just kind of play around with it. The particular data set in question has 32 different markers, so play around with visualizing different combinations of markers for the different gates. Play around with that bin argument because that's ultimately what affects the resolution. Try to see if there's something that will work particularly well in your use case. And with that, I would like to thank you for your attention. If there's any questions, I'll be around in the chat for a little bit. If not, I will see you over at the discussion forums if anything comes up throughout the week. Once again, thank you for your attention. Hopefully there was no audio issues, and if not, I will see you next time.